Look up on a clear night, and the universe presents itself as a vast, silent stage, billions of stars suspended across incomprehensible distances. In 1915, Albert Einstein's field equations changed our understanding of gravity. He proved that space is an active participant in the universe, possessing a geometry that reacts to the matter within it. Look at how this geometry behaves. Massive objects like stars create deep curves in spacetime. That curve dictates how planets orbit and how light bends. We call this gravity. General relativity perfectly predicts the mechanics of the visible cosmos, from orbiting planets to collapsing stars. But a century later, a glaring problem remains. We have absolutely no idea what the vacuum of space is actually made of. Think of a piece of cloth. From a distance, it looks like a single continuous sheet. But if you zoom in close enough, you find individual woven threads. Space-time, as Einstein described it, lacks those underlying threads. When physicists try to mathematically calculate the granular substructure of space, the equations of general relativity simply break down. They give impossible answers. To find the physical blueprint of reality, we have to leave the macroscopic world behind entirely and look down to the absolute smallest physical scales. Defining this underlying structure represents the search for the core of physical reality, an attempt to see how the vacuum of space actually holds itself together. We start by moving inward. Using a logarithmic scale, we drop rapidly from the cosmic vacuum, anchoring our trajectory right here on Earth. Down past the familiar human scale, slicing through biological membranes, and plunging directly into the invisible subatomic void. The smooth, predictable curves of general relativity do not exist down here. The microscopic world operates under the highly erratic rules of quantum mechanics. At this scale, particles behave in ways that defy classical logic. The most prominent example is quantum entanglement. The challenge for scientists is figuring out how these chaotic, unpredictable microscopic forces somehow construct the smooth, orderly cosmos we observe above. Einstein famously called entanglement spooky action at a distance. Two isolated particles can instantly mirror each other. A change to one affects the other, regardless of the vast distance between them. Many physicists now suspect that entanglement acts as the structural mechanism for space itself. Stanford physicist Leonard Susskind proposes that these specific quantum connections create spatial connectivity. The entanglement between particles literally sews reality together, producing the familiar curves of spacetime. Entanglement is the underlying thread. The microscopic bonds between particles weave the physical geometry of space into existence. Taking this radically new quantum perspective, we can rapidly scale back up from the microscopic world to the immense cosmos. We can look at extreme gravitational environments, like a black hole, and evaluate them through this network of quantum threads. Viewing space as a physical, entangled network provides a potential mechanism to solve complex cosmic mysteries, including the troublesome black hole firewall paradox. Suskind's framework allows the chaotic mathematics of quantum mechanics and the extreme gravitational equations of a black hole to finally coexist without breaking down. By redefining the foundation of space, physicists can finally account for the extreme gravity of a black hole without discarding the rules of quantum mechanics. This framework brings us closer to quantum gravity, the elusive unification of Einstein's macro-reality and the subatomic quantum world. The concept of spatial connectivity built through entanglement is our most promising step toward achieving that unification. For centuries, humanity viewed space as a static, empty stage. Now, the math points toward a hyper-complex, intricately stitched quantum fabric. To understand the largest, most immense forces in the universe, we have to map the invisible, microscopic ties that bind them together.